Hello everyone, I am Pushpita Chanda. I am a TA for. Hello everyone, I am Pushpita Chanda. I am a TA for this course, Laser Introduction, Introduction to Laser for Saturday. So let us discuss today some basic things which are not only related to the laser technology. It's like some basic physics. So let us discuss today spectroscopic terms. Okay, so first some basics terminology. Immunology, state. So what is a state? The state of an atom is the condition of motion of all the electrons. It is specified by listing four quantum numbers of each electron. Okay, the four quantum numbers we will discuss. Several states have same energy. They are said to be degenerate. And the state with the lowest energy is the ground state. So the state of an atom, we can say it is specified by four by listing four quantum numbers for each electron. Okay. Then the next is energy I hope I am audible and the screen is visible now. If not, you can say it in the chat box. The next term is energy level. Okay. It's called a collection of states having the same energy in the absence of external magnetic or electric field constitutes an energy level. Okay, an energy level is quantized by a quantum number J. What is J? We will see a little bit later. External magnetic or electric field constitutes G level. The most important thing is in the absence of external magnetic or electric field, the energy levels got changed in the presence of electric and magnetic field. There is another thing called sublevel, which is when an external field is applied, the energy levels split, and the each level splitted into several sublevels. So, in the presence means of some external field, sublevel appears. Then we'll go into called town. What is a town? A spectroscopic term is defined by this 2s plus 1 Lj. So when you want to write a specific level, energy level, you write that level as this nomenclature. This is called spectroscopic term. The next called configuration. So when we write N and L's for, sorry, this will create confusion. N and S for all the orbitals of the atom is called configuration. Then a term for equivalent orbitals. Okay. So the orbitals which have N and L's are same is called equivalent orbitals. Okay. And the electrons are called equivalent electrons. The electrons are okay. And now this thing called multiplet. Okay. This is called a collection of transition between two terms is called multiplets. So a multiplet is consist of number of lines. One transition is line. A collection of transition is called multiplet or line, or you can call singlet also. So now we dive into the thing that how these spectroscopic terms become calculate, right? From the electrical configuration and all. Okay. Terms, or we can say spectroscopic terms, is obtained by adding together the angular momentum vectors are spin angular momentum, orbital angular momentum. Spin angular momentum is L. Oh, sorry, S. S. Orbital angular momentum is L. By adding these two terms, spin angular momentum and orbital angular momentum of the individual electrons, we get the spectroscopic terms. Okay. So when we see things mechanically, or even in classical mechanically, we need to write Hamiltonian for each system. So when we write Hamiltonian for a atom, it consists 5 terms. Okay. First is called the kinetic energy of all the electrons. This is like 1 to n. We assume that there's an n number of electrons. Ei squared by 2m. This is the kinetic energy term. The next term is called electrostatic energy of the electrons due to interaction with the nucleus. It is written as minus. There should be a minus term. That is 1 by 4 pi epsilon naught Ze. This is the charge of the nucleus into charge of one electron, E by Rij. No, okay, that's Ri. Should not be actually. 12 Ri. The third term is the mutual electrostatic energy of electrons. That is the interaction between one electron with another, not another with every other. Okay, that term is positive because here it is negative because Ze is positive and one electron in minus E. So together minus Ze square. But here it is minus E into minus E. So together that will be plus E square. So this term is plus. And there will be second double quotation. I is from 1 to n. J is from 1 to n minus 1. 1 by 4 pi epsilon naught E square Rij. Sorry guys, there is a technical glitch. Okay, I'm trying to solve it out. Okay. Let us resume our discussion. That that is 1 by 4 pi epsilon naught Z E into E Ri. The third term is mutual electrostatic energy which is I1 to n j 1 to n minus 1 1 by 4 pi epsilon naught E minus E into minus E by 4 ij. And the fourth term, hello, what happened? Spin, spin correlation term or energy. Let's not use the thing term because it will be confusing. Energy. Okay. The fourth term is spin orbit interaction. Okay. So, uh, spin is like is then L plus S, and spin orbit interaction we call it JJ coupling. Okay, for most of the atoms, mainly the lighter ones, spin correlation term are the largest of the remaining terms. And this term spin orbit for lighter atoms, spin correlation term is greater it, than spin orbit. And then we consider LS coupling, or we obtain terms via calculation of LS coupling. But for heavier atoms, then that spin orbit interaction terms predominates. Then we consider JJ coupling. Okay, so let us discuss LS coupling. So in LS coupling, first, what are the steps? First, the spins are considers. Okay. Then second, spin or spin angular momentum. Okay. So S1 and S2 from the electrical configuration S1, eh, S2, S3, and so on, they are considered and they are added. So total S value can belong from this S1 to S2 to S3 minimum to however configure combination we can create by S1, S2, S3 by plus and minus minimum to maximum. So for two electrons in the last orbital, or say we can discuss the examples, S1 and S2, minimum will be S1 minus S2 and maximum will be S1 plus S2. So anything that any value between S1 minus S2 to S1 plus S2 will be the capital S. In the spectroscopic term 2S plus 1 Lj, this denotes multiplicity. City. Okay, and this is that. Then we add the L terms. L terms, like capital L will be L1 plus L2 plus L3, so on, minimum from minimum to that is maximum. Yeah, for two turns. For three turns, S1 minus S2 minus S3 and S1 plus S2 plus S3. Now I will explain with the like example. Yeah, I will explain. And first, I want to explain the steps of the LS coupling. First, you need to add the spin angular momentum, then add the orbital angular momentum, then I'll come to that. And this L is corresponds to Lj, this L. Lastly, we need to add that spin orbital angular momentum, spin angular momentum and orbital angular momentum, and obtain the J. So okay, first we like do some examples. When we suppose there is only one electron, so like S is equal to half, so capital S will be half because no other electrons are there. So the minimum is half, also the maximum is also half. Okay, so 2s plus 1 will be 2. This corresponds to doublet. Okay, we have I have already addressed that 2s plus 1 is called multiplicity. So here multiplicity is 2. Okay, if there is 2 electron, so s1, then we add, right, s1 is equal to half and s2 is equal to half. Then s will be what? Half, from half plus half to half minus half. So half plus half will be 1 and half minus half will be 0. So in this case, 2s plus 1 will be 3 or 1. Okay. So it called singlet. This is called triplet. Okay. Now 3 electrons. Okay. For more than 2 electrons, we need to do it on a bunch. Like for 3 electrons, we for like there is S1 half, S2 half, and S3 half. So first we need to determine S1, S2 minimum, which will be half minus half, 0, and S1 plus S2 maximum, which is half plus half is equal to 1. Then let's call it S dash. So now we will obtain S dash plus S3 minimum, which can be C0 plus minus half, and minus half, it's like spin up. If plus half is spin up, minus half is spin down, so it is half. Always we take mod value. And S dash plus S3 maximum, it will be 1 plus minus half. So there can be two value, 3, 2 and half. So the maximum is this. So for 3 electrons, there is 3 values. Half and half. These two are same. For 3 electrons, these two are same. So it's basically 2 values. So S can be 3 by 2 and half. From 3 by 2, we get 2S plus 1 is equal to 4. And for half, it's become 2. So it is called doublet, we know that. But this is called quartlet. For 4 electrons, okay, we do it on a bunch, 2 by 2. Or here we have already done like 3 by 2 and half. So we can take 3 by 2 and half and add plus minus half. This will give a one combination, and this plus minus half. So this will give 0 and 1, and this will give 2 and 1. So there will be three kind of F's. 2, 1, 0. Okay, so 2S plus 1 values corresponds to them when S is equal to 2 is 5. When S is equal to 1, this is 3. And when S is equal to 0, it is 1. Okay, so this is called quintet. This is called triplet. And this is called singlet. So that's how we add S. For L, this is singular. But for L, we do not consider half. Like for S, when we write electrical configuration, we write S, P, D, F, G, H, I. Sorry. I. So for S, small l is equal to 0, 1, 2, 3, 4, 5, 6. That's why. So for L1 plus L2, 2 for 2 electron L1 minus L2. This will be L. For more than 3 electron there, first we compute for 2 electron, then we add third one, like this. So for example, we compute 3p and 3d electron. Okay, for p, L will be 1, and for d, L will be 2. Okay, so L1 plus L2 is 2 plus 1, 3, and L1 minus L2 is 2 minus 1 is equal to 1. But it's not only L1 plus L2 and L1 minus L2. The L is from L1 plus L2 to L1 minus L2. So from 3 to 1. So 3, 2 and 1. Even here for J, L plus S, it is like L plus S to L minus S. Another example is 2p, 3p, 4d electrons. Okay. So for p, L is 0, sorry, 1. And again 1, D is 2. So L1 is equal to 1, L2 is equal to 1, L3 is equal to 2. So L1 plus L2, 1 plus 1, L1 minus L2 will be 0. So L1 plus L2 plus L3, 2 plus 1, 3, and 2 minus 1, 2. So we need to calculate only minimum and maximum. We have here got maximum is 3 and minimum is 0. So 0 to 3, all values will be counted. Okay, there is a difference. Sorry, I made a mistake. Here it is 2 plus 2 and 2 minus 2. So 4. So we got 4 value, 2, 0, 3 value, 2, 0, 0, 4. So the minimum is 0 and the maximum is 4. So it varies from 0 to 4. So all the possible L values is 0, 1, 2, 3, 4. So there is possible 5 values. So it S, P, D, F, G. Sorry for the interruption. Okay. So it's 0 to 4. So values is 4, 3, 2, 1, 0. So this is called S, P, D, F, G. Similarly, the J values that is from L plus S to L minus S values. So So we know when S is something, the total number of S is 2S plus 1. This is called multiplicity. When there is some L, like for S orbital, there is 2, like there is one, like in S orbital, only 2 electron can reside, one spin up and one spin down. Only one suborbital. For P, this is 3. And for each or that is called basically Px, Py, and Pz. So for each like room, you can see that only 2 electron can stay up and down, up and down, and up and down. So 3 into 2, 6 total. 6 electron can stay in p orbital. For D, there is 5. And so total 10 electron can stay. So multiplicity for L is also 2L plus 1. For S, L is equal to 0, this is 1. For P, this is 3. For D, that is 5. Okay, right. So what will be the multiplicity for J? So when L greater than S, the multiplicity will be 2S plus 1. But when L less than S, the multiplicity will be 2L plus 1. This is the multiplicity of J. Of J condition when under multiplicity. Sorry, yes. So there comes a rule, which is Landé interval rule. Okay, what does the rule say? The rule says the energy level or interval or spacing between consecutive levels j and j plus 1 of a fine structure multiplet is proportional to j plus 1. That is, to the larger of the two j values of interval. So it says that what will be the fine structure interval ratio. So let us assume there is three terms: 3D1, 3D2, 3D3. Okay. So here you can see the 3 come to s plus 1 is equal to 3. So s is equal to 1. Right. So what will be the separation between these three? The separation between this will be between 3D1 by 3. Okay, sorry. 3D2. The separation between these two will be 2, and the separation between these two will be 3. It's not only 2 and 3. It's like we can have calculation. It contains some other terms, like we can say that j is equal to L plus S. Okay. Now we want to have a product j dot j. So what will be the product? L dot L plus S dot S plus 2 L dot S. So it can we say j dot square L square plus S square L dot S. So L dot S will be half of j square L square S square. Okay. So the energy level gap. The energy level gap can be calculated from the L dot S, because that is also a calculation, but it is will be equal to A by 2. It's actually proportional to L dot S. So this term can, we know J square is J into J plus 1 into H cut whole square from eigenvalue relation. Square is L into L plus 1 square. Similarly for S. So this term will be J into J plus 1 minus L into L plus 1 minus S into S plus 1. H cut square. So energy difference spacing between two level is A j into j plus 1 L into L plus 1, S into S plus 1. Now to consecutive level, 2j plus 1 minus j. So j plus 1 into j plus 2 minus L plus 1 into L plus 2 minus S plus 1 into S plus 2 minus A j into j plus 1 minus L into L plus 1 minus S into S plus 1. After all this calculation is come like A j plus 1 into j plus 2 minus j into j plus 1, and that is 2a j plus 1. Here one assumption has been placed, that is that the fine structure level of a multiplet have the same values of L and S. Okay, so the L into L plus 1 and L plus 1 into L plus 2, they have same combination. Whereas we have written that is L plus 1 into L plus 2 and here minus L into L plus 1, but the values, they didn't differ. So here comes the energy spacing, what I have been like, the spacing between these two will be less compared to this two. Similarly, the spacing between 4d half, 4d t by 2 and 4d 5 by 2, 4d 7 by 2 what will be that? So this spacing is 3, this is 5, this is 7. So 3 is to 5 is to 7. This is for Landé interval rule or Landé interval rule. Now, let us discuss some Ellis coupling rules. For one electron, one optical electron, say one S. So S1 is equal to half. So S will be half. Multiplicity 2S plus 1 will be 2. L is 0 for S. So J is L minus S to L plus S. So it's basically half plus 0 to half minus 0, which is half. The spectroscopic term 2S plus 1 Lj here will be 2. L is equal to 0 here. For L, we do not write 0. We write the term S and half. So this is the term. Okay. For similarly, 2S will be the same, 3S will be the same. Okay. Like for ground state, configuration of lithium is 1s square 2s. So it is a closed subshell. So only 2s term will provide optical translation and all. So the spectroscopic term for this will be 2s half. Okay. The second configuration is atoms with 2 or more non-equivalent optical electrons. It has assume 4p 4d. Okay, so S1 is equal to half, S2 is equal to half, L1 is equal to 1 for P1, for DL2 will be 2. So S from S1 minus S2 to S1 plus S2. So it is 0, 1. And L be L1 minus L2 to L1 plus L2. So that will be 2 minus 1 to 2 plus 1. So 3 to 1 combination will be 3 to 1. So J will from L plus S to L minus S. So L is 3 to 1, S is 0 and 1. So we have to write combination. S is equal to 0, N is equal to 1, J is equal to V1. So that is 1 P1. S is equal to 0, L is equal to 2. So J will be 2. This is 1D2. Three and 4. S is equal to 1. L is equal to 1. J is 0, 1 and 2. So the term will be 3P naught 3P2. So now, like you can say when S is equal to 1, 2S plus 1 is equal to 3, we call it triplet term. You can see that whenever S is equal to 1, whatever value is L, that, that L is equal, for that L value, we get 3 terms. Here see, whenever there is a value, whatever be the value of L, when S is equal to 0, we get only 1 term. So that's why this is called singlet. And when 2S plus 1 is equal to 1, and this is called triplet. One we get a triplet term. So S is equal to 1, L is equal to 2. So J is equal to 1, 2, 3. So it is 3D1, 3D2, 3D3. When S is equal to 1 and L is equal to 3, J 3, 4. So L is equal to SP. L is equal to 3. So SPGF to know that triplet had which term has higher energy value and which term has lower energy value. For this, we had a set of rules. Okay. That is order of terms and fine structure levels. Okay. First term of the terms arising from equivalent electrons largest multiplicity lie lower. Just 2 is plus 1. Terms multiplicity and arising from equivalent that with just L value lies lowest. So which terms has largest S, it will be at the level, and which has largest L at a given S, it will have lower. It will stay in lower. Then 3A will multiplates formed from equivalent electrons in a less than half filled subshell level with lowest J lies lowest. That is, for P, half filled is 3. So when we say 2P2 lowest, J lies the lowest. But when we say 2P4, then the highest J will lie lowest. Okay. On half-filled subshell, they show very slight fine structure splitting. Mhm. The lowest terms arising from the half filled subshells at the best terms and table. These are the rules. Then another rule is there. The terms of a configuration NLQ are the same as the terms of the configuration ML R minus Q, where R is 2 into 2L plus 1. So for L is equal to 1, just P. So this will be for L is equal to 1, that is P. R is 6. So P1 and P5 have the same terms. Only which is the lowest term and which is the upper term, that will change. So back to our previous question, we get 9 terms, like for 4p, 4d. Okay, there is equivalent electron and non-equivalent electron. Equivalent electron and non-equivalent electrons. Like this is non-equivalent electrons. 2 square or 2p2 or 2p4, 4d2. These are equivalent electrons. And for those cases, for equivalent electron, there is an extra layer of conditioning to have this LS coupling terms. Okay. So it is non-equivalent electrons. We get the terms 1p1, 1p2, 1f3. 3p0, 3p1, 3p2, 3d1, 3d2, 3d3, and 3f2, 3f3, 3f4. So how this will stay? So the first rule, first rule says of the terms arising from equivalent electrons, those are with largest multiplicity lie lowest. It is equivalent or non-equivalent electron, whatever it is. So the largest S will lie low. Here 2S is there, 1 and 3. So highest S will lie low and lowest L will be in upper state. So one states will be upper, and for one the largest L will be the low. So F is the largest F. So S is equal to 0 will be at upper state, S is equal to 1 will be the lower state. And this will be divided by this, like 1p, this will be 1d, this is 1f. For S is equal to 1, there is also P will at upper state, then D, then F. But here for P, the lowest, largest J, here we have C, the largest S is at the lowest, largest L is at the lowest, but J, the largest J will not be the lowest. The lowest J will be the lowest. So this will be 3p2, then 3p1, then 3p0. For T will be 3d3, 3d2, and 3d1. For F, that will be 3f4, 3f4, then 3f3, then 3f2. Right. Let us more. Okay. and draw it like so. This made of this. Okay, that is 4P4D. This is S is equal to 0 line. This is S is equal to 1 line. This is 1P, 1D, 1F. This is 3P, 3D, 3F. First one is 3P2, 3P1. This is 3P0. Yeah, this is 3D3, 3D2, 3D1. This is 3F4, 3F3, 3F2. This is the energy diagram. So there are terms of non-equivalent electrons. So this is electron configuration here, and there is terms. If you like calculate, you will get this. SS V1 is 0 and 3 is 1. This one non-equivalent, like it is 1 is 2 is like this, not 1 is a square. Okay. SESP 1P1 1 okay. 3P0 3P1 3P2 SD 1D2 3D 1 2 3. It is like 3D1 3D2 and 3D3 can be written like this. Now look, PP is 1 is 0 1P1 1D2 3 is 1 3P0 1 2 3D 1 2 3. For DD, this is 1 is 0 1P1 1D2 3 1G4 3S1 3P0 1 2 3D1 2 3 3 2, 3, 4, 3G, 3, 4, 5. Okay. We will get these terms. And the close subcells like S2, P6, D10, they form only one S0 terms. Okay. When we consider equivalent electrons, then we will here we are only considering L and S. But when we consider equivalent electron, we consider MS and MLs also. Because for equivalent electrons, the ML and S like for if L is equal to 1, ML is 1, 0, minus 1. S is equal to half. MS is plus half and minus half. So let us say 2s square. So if one electron we are considering half, another is cannot be half. So if for one we need to consider plus half and another minus half. Okay, that's how. So MS plus half and minus half will be 0. And ML, S is already 0. So L is equal to 0, ML is equal to 0. So L is that's L is equal to 0, S is equal to 0. So that's why J is equal to also 0. So we get the term 1 is not. Okay. But if when L is 1 or L it's like other than uh, 1, the things got complicated. And this case will be discussed in equivalent electron LS or JJ Kaplan terms, and I'm not going to discuss those terms. I can mention the terms of equivalent electrons for the simplicity. Uh, so if you want to look into the matter, you can also refer the book Atomic and Molecular Spectral Laser, Rajkumar. P1, P5. So they have the same terms, P1 and P5, I have already mentioned, and they will have half and 3 by 2 for P1 to P3 by 2 will be the lowest. For P5 to P half will be the lowest. P2 and P4 will have again same kind of configuration. P2, 3, P0, 1, 2. Here for P2, 3, P0 will be the ground, and for P4, 3, P2 will be the ground. Sorry, here was this. In P3, it will be 2P, 1 half, 3 by 2, 3D, 3 by 2, 5 by 2, and 4S, 3 by 2. For D1 or D9, 2, 3 by 2, 5 by 2. For D2, this configuration is like this. D2, G4, 3P0, 1, 2, 3F2, 3, 4. They are like this. So now let us say from this we can write a configuration of any atom. Let us say oxygen. So oxygen is 1s2, 2s2, 2p4. So we need to write this these terms because I've already mentioned that 2p4 will be having this spectroscopic terms. So this will be 1s0, 1d2, and 3p0, 3p1, and 3p2. For oxygen, 3p2 will be the ground, and also carbon will have the same configuration because it is 1s2, 2s2, 2p2. This will be the ground. Okay. So the selection rules, they are basically delta L is equal to 0, delta S is equal to 0, delta L can be plus minus 1 also. But for one electron atom, delta L is 0 not allowed. Delta into 0 plus minus 1. But here also j is equal to 0 to j is equal to 0 not allowed. J is equal to 1 to j is equal to 1 is allowed. But j is equal to 0 to 0 is not. So these are like rules of spectroscopic terms. These are basics LS coupling. Let I did not like explain the equivalent atom LS coupling, where we need to like consider MS and SS, MS, ML and MSS. So you can see that in the book, and if you have any doubt, you can ask me. I can explain that later. So move on to JJ coupling. So from LS coupling and from JJ coupling, if you do right, you will get same kind of answer. But for heavier atoms, we do the JJ coupling, or it's not what we do. It's atoms. They interact much more in the JJ coupling scenario. So for JJ coupling, the rule is to first find small j's, which is L1 plus minus S1. So it is from L1 S1 to L1 minus S1. Okay. Then we get capital J by J1 plus J2 to J1 minus J2. So for LS coupling, first the spins couple in there, the spin correlation was strong, then orbits were correlated, then spin and orbit. But for JJ coupling, as I have mentioned earlier, that spin orbit term, like first we do add L1 plus S1. That's mean we like the in the atoms, spin and orbit coupling happens first, then those J's couple. So same like example 4P and 4D. So for P electron, L1 is 1 is 1 is half. So J1 is equal to L1 plus S1 to L1 minus S1. So it is 3 by 2 and half. Between 3 by 2 and half, there is no other term. Like from L1 S1 to L1 minus S1, gapping should be 1, not half and all those things. So 3 by 2 minus 1 is half. If it has been 5 by 2, the maximum is 5 by 2 and minimum is half. Then 5 by 2, 3 by 2 and half will be considered. So J1 is 3 by 2 and half. And for the D electron, 2 is equal to 2, S2 is equal to half. So J2 is 2 plus half. 2, 2 minus half. So that is 5 by 2 to 3 by 2. So this is only 5 by 2 and 3 by 2. Okay. So J1 is 3 by 2 and half. J2 is 5 by 2 and half. Now we couple J. So there is a combination can form 3 by 2 and 5 by 2, 3 by 2 and 3 by 2, half and 5 by 2, half and half. Okay, that gives 3 by 2 plus 5 by 2, which is 8 by 2, that is 4, 2, that is 5 by 2 plus 3 by 2, and 5 by 2 minus 3 by 2, 1. 4 to 1. So 1, 2, 3, 4. This j gives 0 to 3. So 3, 2, 1, 0. This j gives 3 and 2. And this j gives 0 and 1. So these are the levels. This level can be drawn same as LS coupling levels. That is, again, 3 by 2, 5 by 2, then 3 by 2, 3 by 2, then half, 5 by 2, then half, 3 by 2. Here also j splitting will be there. J is equal to 4, j is equal to 3, j is equal to 2, j is equal to 1. And this will be 3, 2, 1, 0. This will be only 3 and 2, and this is 2 and 1. That's how the coupling will happen. The selection rule is here. That is delta j 0 and plus minus 1. But j from 0 to j is equal to 0 is this transition is not allowed. Same as the LS coupling. Okay. Is the thing. Let us some question. What will be the question? The quantum numbers of two optical electrons in a two valence electron atoms are, that is given. So one work is less. You need not to find L and S. They are given already. Instead of 2p, 4p, 6d, they have given this 5 to 1 is equal to half. So we need to find LS coupling terms. So L1 plus L2 to L1 minus L2, that will be L will be 3 plus 1, 2, 3 minus 1. So 4 to 2. L will be 3, 4. And S will be S1 plus S2 to S1 minus S2. So for 2 electrons, it will be 1 and 0. already like shown it earlier. We can go back. So we have two combination. H is equal to 0 and 1, and L is equal to, sorry, L is equal to 2, 3, 4. So when S is equal to 0, L is equal to 2, J is equal to 2. S is equal to 0, L is equal to 3, J is equal to only 3, S is equal to 0, L is equal to 4, J is 4. But when S is equal to 1, J is equal to 2. Okay, sorry, L is equal to 2. So J is equal to 3, 2, and 1. 1, L is equal to 3. J is equal to 4, 3, 2, and when S is equal to 1, L is equal to 4, J is equal to 5, 4, 3. And write this V1 SPD SPD E B SPD F F F and G4. This is 3 D1 2 3 3 F 2 3 4 and sorry, it is 3 G 5 4 3. And here can come a question, what is the ground state? So first the simplicity multiplicity will be the 1 and L will be the highest, then J will be the lowest. So 3G3 will be the lowest term, ground state. Is the answer. So that's all for today. See you in the next class.